If large enough stress is applied, metallic materials can deform plastically, which is an irreversible process. The plastic deformation is usually mediated by dislocations, which are line-like defects in the crystal lattice. If stress is applied to the sample, the dislocations start to move from the interior of the sample towards its surface. Due to high dislocation density, typically more than 10 to the power of 13 dislocations per square meter, the deformation of bulk metallic materials usually appears as a smooth process, both in space and time. This is seen in the so-called deformation curve, showing how much stress is necessary to achieve a certain level of deformation. During the deformation, the collective movement of dislocations causes emission of ultrasonic acoustic waves. Now, you can hear an example of such an emission transformed into the audible frequency range. Let's now fabricate microscopic samples by bombarding the material's surface with a focused beam of gallium ions and deforming them using a nano indenter. On a micrometric scale, the deformation looks completely different than on a large centimeter scale. Sudden, unpredictable stress bursts appear on the deformation curve, which are well correlated with acoustic emissions. A unique experimental setup was developed by our team to examine in depth the dynamics of deformation on microscales. In our experiments, the deformation of micropillars is carried out in the chamber of a scanning electron microscope, abbreviated SEM, and the concurrent acoustic emissions are recorded by a piezoelectric transducer. Such a unique blend of experimental techniques allows us to simultaneously collect 3 different types of information. First, stress and strain data using the nano indenter. Second, high time resolution acoustic data recording. Third, high spatial resolution visual images using the SEM. Let's now have a look at a real experiment. The red curve represents the time evolution of the force, stress. The blue and yellow curves are related to the acoustic emission activity, which you can also hear. On the right side, the corresponding video of the micropillar deformation is shown. It is obvious that the correlation between the appearance of slip bands, the stress bursts, and the acoustic emission activity is very robust. Despite the huge difference in spatial and temporal scales, we can find a remarkable similarity between earthquakes and micropillar deformation. In both processes, the probability density of released energy, E, decays as a power law with an exponent approximately -1.7. In seismology, this relationship is known as the Gutenberg-Richter law. In summary, the most important results are as follows. We construct a unique experimental setup which can detect weak acoustic emissions of dislocation slip during the compression micropillars. In combination with concurrent electron microscopy observations, the plastic deformation can be characterized by high spatio-temporal resolution. The statistical analyses show that despite fundamental differences in deformation mechanism and involved length and time scales, dislocation avalanches and earthquakes are essentially alike.